Hi, my name is Amelia Kopp, and this is the Physics 2211 Lab 4. Lab 4 is all about oscillations. The point of this lab is to model the motion of a mass on an oscillating spring. First, we're going to introduce comparative analysis between the graphs of motion and energy. Initially, we're going to be looking at changes in kinetic energy, potential gravitational energy, and potential spring energy. Then, we're going to look at the predicted versus observed motion related to position. We're going to be keeping a focus on Newton's second law, specifically that the net force is equal to mass times acceleration. For our calculations today, we're going to be putting into use the equations T is equal to 2 pi times the square root of our mass over our spring constant K. We're also going to be looking at F of S is equal to negative K times X. F of G, our gravitational force, is going to be m times g. We're using this since the spring is close to the surface of the Earth. Delta U, US is equal to 1/2 K S squared. This is our potential spring equation. U of G, our potential gravitational, is mgh. Again, we're using this equation because we're looking at a spring close to the surface of the Earth. Finally, our kinetic energy is equal to 1/2 mv squared. Next, let's take a look at our intuitive equations. As discussed before, F net is equal to mass times acceleration. We're going to be looking at our position update formula. And we're going to be looking at our velocity update formula. Both of these are going to be important whenever we take a look at our GlowScript code. Looking at our GlowScript code to begin with, we can see this section of code defines our fundamental equations that are the basis of our lab. Specifically, our force spring is equal to negative K of the spring times L hat times our stiffness, and F net is going to be equal to our gravitational force plus our spring force. We also are going to take a look at our three energies put together in our total energy equation. That's our kinetic energy, our gravitational potential energy, and our spring potential energy. All equations discussed earlier in this video. In this block of code, we can see the updating formula for velocity here and position here. This is going to be what we see in our video whenever we run our code. On the graph to the right, we know that delta U is equal to the green line plus the red line indicated here. Specifically, our red line is going to be our potential gravitational force, and our green line is going to be our potential spring force. Our blue line represents our change in kinetic energy, and our yellow line is going to represent the change in total energy in our system. Using our total change in energy is equal to the change in both delta U's, which breaks down into our spring force and our gravitational force, plus our change in kinetic energy is equal to 0. That's why we see that our delta E is equal to this 0 line at the origin. Below this graph in our far right corner, right here, we have our change in observed data versus our change in our observed motion versus our predicted motion. Our observed motion is going to be our blue line and predicted our red line. Finally, we have our end of lab questions. For the first question, yes, the reasoning being that the main proof is that the delta E stays constant at a 0 time, as discussed earlier. This means that no energy is being transferred to or from the system to the surroundings and vice versa, aka our fundamental laws of energy are satisfied for this lab. Finally, for our second question, I calculated the period for x and y to be calculated as seen.